So today, I want to wrap up discussion on lower bounds and then start a discussion on the turnstile model for streaming and sketching the turnstile model. In particular, there we're going to talk a lot about linear sketching. So I mentioned in class on Monday, as well as in the lecture notes, that there are generally two methods of proving lower bounds on sketching algorithms. One is this compression type of argument, which I gave a few examples of on Monday, and there's one more for quantiles in the notes. And the other is communication complexity. So today we're going to talk about that, communication complexity. So the idea of communication complexity is, well, it's a model, okay? It's a computational model where you have two parties. Often they're called Alice and Bob. And Alice has some input. Bob has some input. And they want to compute or determine some function applied to their inputs. And there are variations on this where instead of two players, you might have n players. Each player has their own input, and you want to compute or determine some function of all their joint inputs. That's a possibility. And the model here is Alice and Bob basically talk back and forth. So Alice sends Bob a message, Bob sends Alice back a message, Alice talks back to Bob, etc. And then kind of the last person who receives a message in the conversation then says, aha, I'm now convinced that I know f of xy, and then they output the answer. And the goal here is to minimize total communication. This is communication complexity itself is a very active area where people study various things. So minimizing total communication is one. You can also want to say minimize the number of rounds of communication. That's another thing that people like to do. Or studied in more restricted models where you say, look, I only allow one round, and I want to know what's the minimum message length in one round that's achievable. Or bound the number of bits per round and now argue about the number of rounds you need, etc. So there are various twists on this, but this is the essential idea. Okay. And there are also, I guess, I will say, a few different kind of sub-models. So there's deterministic communication complexity. There's randomized. And within randomized, there's public versus private coin. And another one is, let's say, distributional. Where in these two, the input is worst case, whereas here, the input is random from some distribution. So x and y are drawn from some distribution mu, for example. So you could ask these questions about what's the minimum amount of communication necessary for deterministic protocols that solve this problem, or for randomized protocols that use public randomness. Public randomness meaning there's a public random string in the sky that Alice and Bob both know, and they can both use it to determine what to send. Versus private coin means they each are flipping their own coins privately to determine what to do, but Alice doesn't know Bob's coin flips, and Bob doesn't know Alice's coin flips. Of course, they could share those coin flips by sending it as a message, but that would cost you, right? And you're trying to minimize the number of bits you send. And then distributional is also, basically in distributional model, you can assume without loss of generality that the protocol is deterministic, okay? And the input is random, and you're trying to succeed in computing F with as high a probability as possible while minimizing communication. Okay. Now, Why is communication complexity relevant for proving streaming lower bounds? The basic idea, so the connection between communication complexity and streaming lower bounds So what's the idea here? The idea is basically you'll show that if you'll show a reduction. If computing F is hard in a communication model, then actually let me say it like this. Let me back that up a little bit. Show that, let's say, if can solve problem P, let's say, in string model via an algorithm A, then it's possible to use A in a black box way to solve some function F in the communication model. So we have a reduction. Therefore, if F is hard, meaning it requires a lot of communication, then P must be hard. And typically, of course, you'll see examples soon, the amount of communication in the protocol that uses A as a black box, the number of bits sent will depend on the amount of memory that A uses. So for example, the protocol will be, Alice will look at her input, think of her input as being part of a stream, run A on that stream, take the memory contents of A, send it as a message to Bob, and then Bob can somehow use that to compute the answer to F. So example is F is the equality function on, let's say, 0, 1 to the n. So echo xy is 1 if x equals y and 0 otherwise. So a theorem, which I won't prove today, is that the deterministic communication complexity of equality is at least n. There's basically, I mean, there's a trivial protocol, which is that Alice can just send her entire input. Her input is an n-bit string, send it to Bob as a message, and then Bob can then determine whether x and y are equal. So that's an n-bit communication protocol. And the theorem is that there's nothing better. Even if you allow yourself multiple rounds, there's nothing better. Okay. And now let's use this to show that, again, let's say distinct elements is hard. So following from this, we already know this. We know this via the compression argument, but now we're going to show it using communication complexity. If A is a deterministic exact algorithm for distinct elements, then A uses at least m bits of memory.
Sorry, Jelani?
Yep.
When you say CC of EQ is greater than or equal to n, so what does that mean that it's greater than or equal to n?
Yeah, in fact, it equals n. But when I say CC of F, I mean the minimum number of bits to solve F via a correct deterministic communication protocol. So by a communication protocol, I mean Alice and Bob agree ahead of time on what their protocol is for communicating. Like Alice will tell Bob, okay, like if I get this input, you know, this is the message I'll send as my first message, and if you send such and such as your response, this is how I'll respond to that, etc. They basically know the protocol. The only thing that they don't know is what each other's inputs are. Okay.
Got it.
And then
so
now
the
you
number
want
of
to
bits.
Yeah,
Is the number of bits transmitted?
that's right. Number of bits transmitted.
Got it. Okay.
Transmitted.
What is M here, the theorem?
Oh, there is no M. N. N is the universe size for distinct elements.
Okay. Got it. Thank you.
So, I mean, the proof is going to look very similar to what you saw before. Actually, in fact, let me just be a little more. I think that's, yeah, we can get away with this. So let's prove this. So here's Alice. Here's Bob. Bob has some y, which is in 0, 1 to the n, but you can interpret that as like it's a subset of 1 to n in the usual way. 1 means that the element's in the set, 0 means it's not. Similarly, Alice has some x, which you can interpret as a subset. And then Alice runs the stringing algorithm on the elements of x in sorted order, then sends the memory contents of A to Bob as a message. So this is, well, the number of bits sent is equal to the space usage of A, right? And then Bob can now continue running. Well, first of all, let me do one thing first. The first thing Bob does is first computes, let's call it T, which is A.query, which is just going to equal the size of X, right? So the first thing he checks is, do X and Y have the same size? Okay. If they're equal sets, they better have the same size. If the sizes are not equal, you can already reject and say, no, these are not equal strings or equal sets. And outputs, let's say false, if T is not equal to the size of Y. Okay, and then otherwise, Bob continues running script A on the elements of Y. And then he calls A.query again. Right? And one of two things will happen. If X and Y are equal, then this will just be the size of Y again, right? You won't have added any new distinct elements. If X and Y are not equal, because you know they're the same size, you know that there's something, Y can't be a subset of X if they're the same, a strict subset of X if they're the same size and different. So Y must have an element that's not an X. Therefore, the number of distinct elements will have gone up, and it'll be bigger than the size of Y, which is the same as the size of X. So if T is equal to the size of Y, output true. Otherwise, output false. Okay? Does that make sense? So that's it. And you could ask now, what about, the randomized, so, at the end of the day, are the algorithms that we use for distinct elements in a lot of stringing problems are actually randomized algorithms. So you could ask the question of, okay, can we prove a lower bound on the complexity of a randomized algorithm, even an approximate randomized algorithm for distinct elements? And the answer is, in fact, yes.
Actually, a quick question: do we not care? Because, like, in our proof for the using error correcting codes for the randomized variant, Like it required, the decoder required us to do this exponential search. So do we not care about like the runtime that Bob and Alice use like in this protocol? Like we don't care about like possibly having Bob look at like an exponential family of subsets.
Yeah, we don't care about run. That's right. In communication complexity, we don't charge people for computation. Alice and Bob, internally on their sides, Alice might be solving the halting problem for all I know to determine what message she sends. That's completely allowed.
Great, thanks.
Yeah. And okay, so actually, I just want to say a couple more words about equality. You could look at, for example, the randomized, let's say the randomized public coin complexity in the one-way model. So this arrow means there's only one direction of communication. Alice talks to Bob, and Bob doesn't talk back. So in other words, since there's no conversation, Alice might as well send her entire messages all up front. So there's only one message ever. Alice talks, Bob hears that message. They share a public common string. Bob has to output the answer. And let's say you want to fail with probability at most a third for equality. So this is the minimum cost. I don't know why I should probably fix this. And let's say lock the screen. Okay. So this rpub arrow 1/3 means I want to have a public coin randomized protocol which fails with probability at most a third for equality, where there's a one message only from Alice to Bob. And I want to know what's the cost in transmitted bits of the best protocol, communication protocol that can achieve this. Okay. And any guesses? So we know deterministically you can't do better than n bits, which is completely trivial. Alice can send everything. What do you think you can do in this model with public randomness, with probability a third? Any guesses?
Close to like theta of n.
Theta of n. So it's still basically maybe a better constant, but still linear.
Yeah.
Any other guesses?
The inputs aren't random, right? We're still doing like
the inputs are worst case. That's right.
Yeah.
So I'll just tell you. Yeah. Yes. I guess we.
I think it feels like it should just be it should just be n.
So the answer is that it's actually constant. Okay. And the idea is, Alice. So there's this x that Alice has, which is it's an n-bit string, and there's y that Bob has. Let's say equals then an element of equals. And what they're going to do is there are these public random strings in the sky, right? So they're going to interpret that as like, so let's say there's there's just a bunch of bits in the sky that everyone can see. Okay. What they're going to do is they're going to take the first n bits, and they're going to call that, Z1. They're going to take the next n bits, they're going to call that Z2, etc. This is Z2. And what Alice is going to do is going to send X. Let me actually do this. She's going to send a bunch of dot products. X dot Z1 mod 2, X dot Z2 mod 2, and then X dot Z, let's say R mod 2. And then Bob checks whether, let's say y dot zj is equal to x dot zj mod 2 for all j going from 1 to r. So if any of those dot products are different, then their inputs are definitely different. If any of those, but if all the dot products are the same, that doesn't necessarily mean that the vectors are the same, because maybe the zj just failed to witness the difference, right? But what does it mean what does it mean that y dot zj is equal to x dot zj mod 2? It means that x minus y dot zj is equal to 0 mod 2, right? That's what it means. And if x and y are different, then x minus y is not the 0 vector. X not equal to y implies that x minus y is not the 0 vector. So in other words, x minus y, it might have some zeros, but then it definitely has a 1 somewhere. And then it has some other stuff, which might be zeros and ones. And then you're dotting it with zj, which it has some stuff here. And then it has something here, which is random, and then it has some stuff here, right? What's the probability that x minus y dot zj is 0? Well, none of this matters because it's being dotted with 0. Let's condition on the dot product between these parts, mod 2. That dot product is either going to be 0 or 1. It doesn't really matter. It's going to be something. And whatever it is, the contribution from this part will flip it with probability of half, right? It'll keep it the same with probability of half, and it'll flip it with a probability of half. Namely, if the question mark is a 1, it'll flip it. If its question mark is a 0, it'll keep it the same. So it's 50-50 switch, right? So the probability that we fail to catch x different from y is exactly equal to 1 over 2 to the r, because we did it r times. So every single one of those dot products had to fail to catch it. So if we're just trying to succeed with probability 2/3, in fact, you can just pick r to be 2. And if you want to succeed with probability 1 minus delta, you can pick r to be log 1 over delta. Okay, does that make sense? Questions about that?
So this doesn't seem immediately useful for lower bounds because it looks like this communication complexity is as low as you could possibly want it to be.
That's right.
Do we have to go to private randomness then to get a lower bound?
So that's a good point. So here, we really gave the Alice and Bob a lot of power by being able to share this public random string, right? But if you think about corresponding, what does that mean from a streaming perspective? If I wanted to run like a reduction, if I wanted to like do what I did on the last whiteboard and solve my communication problem using a randomized streaming algorithm, we've been assuming, right, when we talked about, the idealized Flageolet-Martin algorithm and distinct elements in the non-idealized version, one of the components of the non-idealized version was, look, we can't actually store these random, we don't actually have these random hash functions for free in the sky. Whatever hash function we're using, we have to store its representation in memory. That costs us memory. So it's a similar phenomenon here. Look, our randomized streaming algorithm, we can't just assume that all its random bits are stored for free in the sky. It has to pay to store them. So that's more in tune with more in line with the private model of communication, right? So you can ask what happens there. Let's look at our private one-way 1/3 for equality, right? It's not syncing, is it? Let me see what's going on. Oh, testing. Can you hear me?
Yeah.
Yep.
Hello, hello.
Yeah, we can hear you.
Yeah, I finished it like yesterday.
I think there's just some Zoom acted very, something's going on with my speaker. I can't hear anyone. Can someone, if you can hear me, type in the chat? Oh, we can hear you. Okay. For some reason, I can't hear you, though. So can someone type in the chat, were you also kicked out of Zoom, or was it just me? Both my devices were kicked out suddenly.
You know what the .data, .word, and .text stuff does?
Okay, now I can hear everybody. So say that again. Oh,
They
just
say to think about the 4 sections of memory, right?
sorry, I'm just coming back now because for some reason my
But that's
This,
code, static, heap, and stack. But
I don't think you want to be unmuted. Are you in a different Zoom call,
yeah,
Abhishek?
Yeah, I think Abhishek has his mic on by accident.
okay, let me mute him. No, he muted himself. Okay, great.
Sorry
Sorry about that. I don't know. I had some technical difficulty for a second there, but I'm back. So let's look at the private coin complexity of equality. And any guesses as to what this thing is?
Is this a harder problem? So is it n?
It is harder, right? I mean, because now they can't assume that they know each other's randomness. If they want to share what random bits they use, they have to communicate it.
This seems like it should be n, right? Because the thing that are close to n, right?
Right. Yeah.
Good. So I'll tell you, the answer is actually log n.
Log n?
Oh.
Of course.
And you know, it's the the lower bound. So there's a general theorem that says basically that the deterministic complexity of a function is at most something like exponential in the private coin version. So you know we know that this is at least n, right? So that implies that we know that this is true just from that theorem. I'm not going to prove this theorem. But how about the upper bound? So this says that there's a lower bound. How about the upper bound? Upper bound. Alice, right, again, has x. Bob has y. We can treat these x and y as being numbers in the range 0 up to like 2 to the n minus 1, right? They're n bits, so we can treat them as numbers that are n bits long, so they're up to 2 to the n. And the point is, let's look at what we're gonna do is Alice will pick a random prime p in the range from, let's say, 1 to n cubed, and she'll send her number mod p. And then Bob will say yes, say true, if and only if x is congruent to y mod p. Okay.
So she sends the prime as well.
Yes, that's right. She sends x mod p and also sends p, right? Because it's private randomness, so he doesn't know what her p was since he doesn't know her randomness. But the point is now, p is at most n cubed, so sending it takes log n bits. X mod p is at most p, so sending it takes at most log n 3 log n bits. So altogether, we're sending O of log n bits. And the point is, look, if x equals y, they'll definitely be equal mod p. If x is not equal to y, then basically, if x not equal to y, Bob is fooled if and only if p divides x minus y. Okay. But I don't know if you know this from the prime number theorem, but like n has at most O of log n over log n prime divisors. I mean, this is actually not even the prime number theorem. This is just, maybe I'll leave this as an exercise. So the fact that a number has at most log n divisors is pretty simple, because prime divisors, because if you do the prime factorization, let's say the primes are P1 up to Pk, you have that P1 times P2 times P3 dot 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 times Pk is equal to n. You know that each of the Pi's is at least 2. So you know that n is at least 2 to the k. Therefore, k is at most log n. So getting a log n bound is not that hard. I just proved it to you right now. The log n over log n bound, basically the idea is you know that the primes have to be different. They can't all be 2. So you know that the ith prime has to be at least I. So P1 times P2 times dot dot times Pk must be at least k factorial. So you know that n is at least k factorial. And if you just use Stirling approximation or even something simpler, that implies that k has to be at most O of log n over log n. So the point is, you know that if x and y are different, x minus y, let's call this number capital N, x minus y is at most capital N, so it has at most log, roughly log of capital N divisors. So if I pick a random prime, as long as I'm picking from a range that has way more than log n primes, then I'm golden. The likelihood that I'll pick a prime that's a divisor is small. And by the prime number theorem, you can say, look, between 1 and little n cubed, there are a lot of primes. There are roughly little n cubed over log n primes in that range by the prime number theorem. So the probability that I pick a divisor is very unlikely. Okay, so that's that. Right.
Are there problems for which this inequality that you wrote in this theorem, the deterministic communication complexity is less, is basically what this says is the private communication complexity is at least logarithmic in the deterministic complexity.
Yes.
Are there problems for which it's actually equal, like or close to equal, the deterministic?
There are problems where both of them are super hard. Randomness doesn't really help you. We'll see one of those soon. There are even ones where public coin randomness doesn't really help you. The public coin.
Okay, so it's not crazy to think that theta of n would be a possible bound.
There are problems where that is true, where randomness, even public coin randomness, doesn't buy you anything. Okay. It just so happens that equality is like the most extreme example where it achieves kind of the biggest gap that's possible. Okay. So
Jelani,
yes.
Could you quickly just explain what you're saying in the theorem? I don't understand it.
In the theorem?
Yeah, in the statement of the theorem.
Oh, so are you talking about this theorem?
Yeah.
So yeah, you can ask yourself the question of what's the biggest possible gap between the deterministic communication complexity of computing a function versus the private coin, the complexity to compute that same function in the private coin setting with a randomized protocol. And the gap is always at most an exponential gap. You cannot have more than an exponential gap between these two.
I see. Thanks.
Right. And equality is an example where you actually achieve this exponential gap. Okay. So anyway, let's get back to more streaming lower bounds. So let me actually introduce one where I do want to do one at the end where I actually prove the communication lower bounds. For now, I'm just assuming that someone else has proven the communication lower bounds and showing how to use it for streaming lower bounds. So one really hard problem, kind of a canonical hard problem in communication complexity, is what's called disjointness. So here again, I'll just say they have sets. So Alice has a set S, which is a subset of 1 to n. Bob has a set, which is a subset, which T, which is a subset of 1 to n. And disjointness applied to these inputs is equal to 1 if they're disjoint, if S intersect T is the empty set, and 0 otherwise if they're not disjoint. And theorem is that, so here's an example. So what's the most trivial thing that they could do? The most trivial thing is Alice could just simply send her set to Bob, which, just a bit the indicator vector of her set. So a 1 if I is in the set, a 0 if I is not in the set, for I equals 1 to n. That's an n-bit message. So the absolute trivial protocol is n bits. That's deterministic. And the theorem is that even with public coins, and even if they're allowed to talk back and forth, it doesn't have to be one way. The communication complexity of disjointness is omega n. So other than improving the constant factor in the omega, if you use a randomized protocol with public randomness, you're not going to do much better than the trivial protocol. Okay. And now let's look at a streaming problem. Streaming. We see, let's say I1 up to like IL in stream. This defines a histogram. X, where xi is the number of times we saw I in the stream. Okay, so the streaming question is when someone says query, I just want to output the L infinity norm, even up to a factor of 2. Well, let's say up to a factor of, let's say 1.1. So I want to output, let's say some z tilde such that z tilde is guaranteed to be at least the L infinity norm and at most 1.1 times L infinity norm with probability at least 2/3. Okay. And the claim.
So is n the number of distinct elements here?
N is the universe size. So every integer you're seeing in the stream is coming from the set 1 up to n. So just like distinct elements, n means the same thing. So 1.1 approximation of L infinity in the stream with probability at least 2/3 requires omega n bits of memory. Okay, let's prove it. So it's the same thing you're used to. So Alice gets this S, Bob gets his T, and then Alice runs the algorithm on the elements of S, and then sends the memory of the algorithm to Bob, and then Bob continues. Actually, and Alice should send one more thing too. No, actually, that's fine. That's it. And then Bob continues running the algorithm on the elements of T, then queries, then calls a.query. Right? So the possibilities are S and T are disjoint, in which case nothing appeared in the stream more than once. So the L infinity norm is, it's either 0 or 1. 0 is trivial. It means both sets were empty, but it's at most 1. Meanwhile, if they're not disjoint, then there's an element that's in both. So the L infinity norm is 2. So you're deciding between at most 1 or equal to 2. If you have a 1.1 approximation, then that will tell you which case you're in. Okay. So you've now used this streaming algorithm to solve disjointness. The total communication complexity of this protocol is exactly equal to the space usage of A, because the only thing you sent was the memory contents of A. Therefore, the memory has to be at least the disjointness lower bound, which is omega n. Okay, does that make sense?
It's a little weird that this proof and the other proof both for some reason seem to deteriorate when you get an approximation factor of larger than 2. Is there a reason, like a fundamental reason why like 2.0001 is impossible?
Yes, and actually I'll explain that right now. So the bottleneck here was that we were looking at two-party disjointness, but you could look at t-party disjointness.
Wait, can we go back to the previous proof?
Yeah.
So that L infinity norm, is that just the highest frequency of any element?
That's right. Which in this
Okay.
case is either going to be 2 or 1.
Wait, why?
Because, S is a set, so nothing appears more than once in S.
Oh,
T
yeah.
is a
Okay.
set.
Yeah.
Mhm. So t-party disjointness is the following more general problem or generalization. Basically, there's a bunch of players now. There's Alice 1, there's Alice 2, up to Alice T. Each one has their set, S1, which is a subset of 1 to n, S2, which is a subset of 1 to n, etc. And there are 2 cases. You're promised that you're in one of these cases, okay? That's part of the problem definition, is this promise. You're promised that for all I not equal to j, ai intersect aj is the empty set. Or 2, you're promised that for all I not equal to j, ai intersect aj is equal to something, some fixed thing. So they either have all empty pairwise intersections, or there's like one unique person who's in every intersection. So it's even a special case. You could just, the second item 2, you could have just said that they all have something. They all have a shared intersection. But this is even, I'm promising you even more than that. And the claim is that even this is hard. So the theorem is that R pub 1/3 of, I'll call it disjointness NT, meaning that there are T players and the subsets are subsets of 1 to n, is omega n over T. Oh, and I should say what the model, and let's just actually say it in the one-way model. So in the one-way model, the model here is, again, there's a public random string in the sky. Alice 1 sees her input as well as the public random string and chooses to send one message. Alice 2 then, based on that, her input and the random string, sends a second message, etc. This person sends their message. And then Alice T sends the answer. Right? So when I talk about the total bits sent is equal to basically the size of M1 plus the size of M2 plus plus the size of MT minus 1. And of course, a corollary of this is that there exists some player sending omega n over t squared bits, right? Because there are t players, each one sends, in total they're sending n over t bits. Someone has to send at least a 1 over t fraction of that, or 1 over t minus 1 fraction of that, which is omega n over t squared. Okay. So what does this already tell you? This tells you, so a corollary of that is that, let's see, so I guess, is it alpha approximation? So if you have, so here's what I want to say. Right, if in the disjointness case, in the case that they're actually disjoint, you can imagine running a stream on this, right? Where, let's say there's a streaming algorithm that approximates the L infinity norm. Alice runs it on her part, sends the memory contents to Alice 2, who runs it on her part, sends it to Alice 3, etc. in the case where they're all disjoint, the L infinity norm is going to be 1. In the case where there's someone who's in all the pairwise intersections, so who's in all of them, then that person is going to have a weight of t, right? So you're basically, if you have an approximation factor in your algorithm that's t, you can distinguish between case 1 and case 2. Okay, so, and you know that what's the memory. You know that in such a case, some player had to send at least n over t squared bits, but every player is sending the same number of bits, which is just the memory contents of A. So you know that the memory has to be at least n over t squared. So what this says is, if you have an alpha approximation, that implies that you need n over alpha squared memory. Okay. So this is an example where you're not bottlenecked by an approximation factor of 2. You can get hardness even for larger approximation ratios.
By the way, I know it's theta of t, but you actually really only need an approximation that's like t minus 1 over 2, right?
Yeah, something. Well,
or something, or not. It's not going to be t minus 1 over 2. It's going to be like the right multiplicative thing, right?
Right.
It's like
So
going to be t over 2 or something.
If I say like this, z tells
Yeah.
at most alpha times the L infinity norm, and at least the L infinity norm.
Yeah.
Yeah. Then you don't even need to divide by 2.
Yeah.
Okay. One more thing that I'll discuss before I move into actually giving you a proof of a communication lower bound. Let me see. I have a question in the chat. Okay. That looks like we're good. Yeah. So what about estimating the LP norm? Let's say the LP norm. Or 1.1, let's say. It doesn't really matter that much. Remember, the LP norm of a vector is just defined to be the sum of xi to the p all to the 1 over p. It's known that this is a norm for p that's at least 1.
Sorry, Jelani, one question about the
Yes.
last thing we just discussed.
Yep.
I was just thinking, so what we just said is that if we have any randomized algorithm for computing distinct elements, or like this L infinity distinct elements.
Yeah, L infinity. There's no distinct L, just L infinity.
Yeah, L infinity. It requires n over alpha squared memory. Do we know from an upper, like what algorithms actually do we know for this setting?
Right,
Like,
so
is
if you think of alpha as being a constant, then this is really bad, right? This is saying,
Yeah,
if
right.
you want a 1 plus epsilon approximation, which is the kind of thing we've been doing so far, then it's basically saying that there's nothing non-trivial, right?
Right.
So yeah, so this is kind of a big downer.
Okay, gotcha.
Okay, so yeah, in terms of actually achieving this n over alpha squared, I guess we'll see about that later. That there's some, what can you do? How do you achieve n over alpha squared if you wanted to, for example? Yeah, we have not covered that. Okay. Yes.
That was saying there's like nothing non-trivial for L infinity norm?
Sorry, say it again.
Wait, so it was the previous result saying that there's like nothing non-trivial for the
Essentially, right? If you want a constant factor approximation, it's saying that there's nothing non-trivial. I mean, nothing. Definitely you can't do better than shaving a constant factor. You have to be linear in n in your memory.
I remember like a heavy hitters thing from 170. Is that like not the same? Oh, it just tells you what they are. It doesn't tell you how frequently they appear.
No. Well, we're gonna talk about heavy hitters in this course,
Okay.
but it's not. It's a weaker guarantee than L infinity. We'll get there, though. We'll get there. Okay. So what if I want to estimate the LP norm? So what I could do is in case 1 where they're disjoint, that the LP norm. Let's just raise it to the pth power. is the sum of xi to the p is at most n, right? Because each one of these xi's is either 0 or 1. So when you raise it to the p, it's still 0 or 1. There are n of them. Meanwhile, in case 2, you know that there's some guy who appears at least t times. So this is certainly at least t to the p. So if you imagine, you can set, so let's set t to be something like, 3n to the 1 over p. Okay. Then this then would be bigger than 3n. So there's a gap, there's a constant factor gap there, right? So that implies theorem, 1.1 approximation of LP in a stream with a randomized algorithm that succeeds with probably at least 2/3 requires omega n divided by t squared. So that's basically n to the 1 minus 2 over p bits of memory. So this is, non-trivially large for any p which is strictly bigger than 2. And it turns out this is tight, maybe surprisingly. Indick and Woodruff in 2005 showed an algorithm achieving, poly 1 over epsilon times O tilde. O tilde is hiding log n factors, n to the 1 minus 2 over p memory for 1 plus epsilon approximation. So somehow this magic exponent is exactly the right answer up to log factors.
Why do we get to decide that t equals ceiling of 3n to the 1 over p?
Because we get to decide which, remember, how do we show hardness of the streaming problem? We reduce from a hard problem, right? And we get to choose which hard problem we reduce from. So let's reduce from the disjointness NT problem where t is this.
Okay.
Okay. So now enough of taking communication lower bounds for granted and using them. Let's see how you can actually prove a communication lower bound. So proving a communication lower bound. So what I'm going to show you is that there's a problem that's called indexing. In fact, even a version called augmented indexing. I'm going to show you that this is hard. Okay, we're going to prove that. And then we're going to show that this reduces to a problem called gap hamming. Therefore, gap hamming must be hard. And gap hamming reduces to, let's say, 1 plus epsilon approximation of distinct elements. Therefore, 1 plus epsilon approximation of distinct elements must be hard. And in particular, we're going to get out of this in omega 1 over epsilon squared bit lower bound for 1 plus epsilon approximation of distinct elements, which is actually the right answer. You can achieve 1 over epsilon squared bits. So the right answer is 1 over epsilon squared plus log n bits. This is the optimal upper bound. Okay. So maybe I'll do this in reverse order. So I'll define what these problems are, and then I'll show the reductions in reverse order, and finally show that augmented indexing is hard. Okay, so what are these problems? So indexing, Alice gets a subset S of 1 to n. Bob gets an index I between 1 and n. And there's only one message sent from Alice to Bob, so it's one-way communication. And indexing Si, comma I is equal to S sub I, or actually, let's actually write it. It's more convenient to write this as a string. So let's say this is x and 0, 1 to the n. So right, it's just the ith bit of x. So it's intuitive, intuitively, and let's say there's public randomness. Intuitively, look, there's only one message that Alice is sending. Alice has no idea what index Bob is holding, right? So what can Alice really do other than send her entire string to Bob? Okay. And in fact, that is true. So the theorem is that our pub in the one-way model with probability, let's say failure probability delta of index is at least, it's omega n. In fact, it's this 1 minus binary entropy function applied to delta times n. And if you haven't seen this H2, the binary entropy function applied to P is let's say minus P log P minus 1 minus P log 1 minus P. And you can plot it. Let's say this is, it only makes sense when P is between 0 and 1. So here's 0, here's 1, here's a half. This kind of looks like this. Good. So if you think of in particular, this is always at least omega n, no matter what delta is. For any delta less than or equal to half, this is at least omega n. So something looks a little, yeah.
Isn't this a little funky because if I take delta, so delta is the failure probability, right?
Yeah.
And if I fail, if I want that failure probability to be small, I would expect that this thing would get closer to n.
And that's what happens, right?
Right,
Binary,
but then,
yeah.
but it goes, but on both sides though, right? Of 1/2.
Yeah, but this theorem assumes that, if delta, so this theorem is assuming that delta is at most a half. So I should have put this here. If delta is at least a half, this is completely a trivial problem because if I'm willing to fail with probability a half, Bob can just flip a coin.
Oh, these are binary strings, right? So it's not,
binary.
yeah. Oh, okay, yeah. Okay, fine. Okay, got it.
So this is the indexing problem.
Yeah.
Okay. Gap Hamming. Alice and Bob again get some strings as input. And they're promised in one of two cases, either the Hamming distance. We talked about Hamming distance when we talked about error correcting codes, just the number of entries where they're different. You're told that either the Hamming distance is at least n over 2 plus root n, or the Hamming distance is at most n over 2 minus root n. And you have to decide which. And the theorem is that R pub of this thing is also omega n, or omega n. Okay. So is that clear in terms of the
Is there a reason?
Is
there a reason for this plus minus root n window that we're looking at?
Yes. You mean as opposed to simply determining whether it's better?
I could take it to be just some epsilon, right? Like n over 2 plus minus epsilon. But why do we take it to be, what is so special about root n?
Yeah. So I guess I'll prove to you that it's hard. So you'll see in the proof where that comes up. We're going to make use of that root n we're going to make use of the definition of the problem when we prove that it's hard, and that root n is going to play a role. Okay. Good. So let's now move to reductions. So remember the picture, I said that we have indexing, reduces to gap hamming, reduces to 1 plus epsilon approximation of distinct elements. So now we're going to show that gap hamming is hard, implies that distinct elements is hard. Okay. So we're doing a reduction. So take a gap hamming instance with strings of length 1 over epsilon squared. We know that, therefore, the complexity of that problem is omega 1 over epsilon squared, right? That's what we said on the last slide. It's omega, the vector length. So now Alice runs, it's the same story as usual. Alice runs, so now let's say that we have a really good streaming algorithm which provides a 1 plus epsilon approximation. Alice runs that algorithm on the I such that xi is equal to 1, and then sends the memory to Bob. Bob continues running. On the I such that yi is 1. And actually, let's also sends the memory of Bob, as well as sends 2 things. The other thing she sends is the support size of x, the number of ones. So Alice's message is, or her message length is, what's the support size? It's a number between 0 and 1 over epsilon squared, because the length of x is 1 over epsilon squared. So writing that, telling me which number it is, takes log of 1 over epsilon bits, or log of 1 over epsilon squared bits, which is the same as 2 log 1 over epsilon. So Alice's message length is, at most, 2 log 1 over epsilon plus mem a bits. And I'm going to show you that you can use this message to solve gap hamming. We know that gap hamming requires omega 1 over epsilon squared. So that will imply that mem a, the length of the memory of a, is at least this omega 1 over epsilon squared minus 2 log 1 over epsilon. But of course, log 1 over epsilon is much, much smaller than poly 1 over epsilon. It's much less than 1 over epsilon squared. So this is omega 1 over epsilon squared. Okay. Does that make sense? That's where the lower bound is coming from. And yeah, I mean, I guess the point here is, for us, this additive root n, right? You basically have to decide a difference in terms of, you have to decide a difference of an additive root n in the Hamming distance, right? And the point is just, if n is 1 over epsilon squared, then root n is 1 over epsilon. So basically, the idea here is just, if n is 1 over epsilon squared, then root n is equal to 1 over epsilon, which is the same thing as epsilon n, right? So if you're able to determine the Hamming distance up to an additive epsilon n, if you're, basically the idea is, look, if I can solve distinct elements, I can use that to determine an additive 1 over epsilon and decide the difference between these 2 cases. Does that, so back to your question about why the root n, does that answer your question? That like
Yeah,
why?
yeah.
Okay. Okay. So I think I don't have a whole lot of time left. So I'll just assert, and you can check the notes. I'll just assert, check notes if you want, that the 1 plus epsilon approximation of distinct elements will let you decide the Hamming distance up to additive 1 over epsilon, which is exactly what you're trying to do here. And now let's try to prove that gap Hamming is hard based on indexing. So this is what I said before. Okay. So the proof.
What was our bound for index again? Can you? It was
It's also
n,
linear.
right?
It's also
Yeah.
linear.
Okay.
That's right. So let's do the following. So I'm starting off with an, so I need to show, so I'm gonna reduce indexing to gap Hamming, right? So what does that mean? Alice has an x, Bob has an index, and Bob wants to know what is xi. So here's what we're going to do. Or you can think of it as Bob has, let's say, some EI, where I is, I is in 1 to n, right? EI is the ith standard basis vector. In the ith position. And what they want to know is the dot product. Okay, same thing. So they're going to use public randomness here. And first of all, Alice is going to convert her string into some x prime, which is in -1, 1 to the n, where xi is +1 means xi prime is -1, and xi is 0 means xi prime is +1. So she's going to interpret zeros as ones and ones as -1s and convert her binary string 0, 1 to the n into a -1, 1 to the n string. Then the public randomness let's say that I'm doing gap Hamming on strings of, because there are 2 different n's here. Those for indexing and gap Hamming. So let's say that gap Hamming on capital N bit strings is omega capital N. And now I want to solve indexing on a little n bit string. And I'm going to reduce that to gap Hamming on a capital N bit string, and capital N is going to be, it's going to be theta little n. Okay, so good. Where was I? So public randomness, they're going to, in the sky, they have this randomness that's going to specify some R1, which is in -1, 1 to the n, R2, which is in -1, 1 to the n, all the way up to R capital N, which is in -1, 1 to the n. And then Alice is going to turn x prime into the vector with all these different dot products. X prime dotted with R1, X prime dotted with R2, X prime dotted with Rn. And then Bob is going to do the same thing. He has EI. He's going to turn that into EI dotted with R1, EI dotted with R2, EI dotted with Rn. By the way, of course, this is just, of course, the ith entry of R1. This is just the ith entry of R2, etc. And the claim is that, so now there are these two strings. Let's call this string, let me give them names. This is string A and B. Okay. And these are capital N bit strings. That actually, let me just make sure I should have put the sign of this. So all these are signs. So this is the sign. All these are the sign of the dot product. And just so I don't have to worry about, like, what if the dot product is 0? I'm gonna say that n here is odd. I'm going to reduce from indexing where little n is odd. That way the dot product is never going to be 0. And the claim is that if I can solve gap hamming between little a and little b, with high probability, that's going to let me recover the solution to indexing. Okay? So let's keep going. So what does Bob have in his hands now? Bob has this b, which is in -1 to 1 to the n, and b is equal to the ith bit of R1.
I think you want capital N, right?
Yes. The ith bit of R2, the ith bit of R capital N. And we're looking at the Hamming distance between this and what Alice has. She has her little a. And A is all these signs of dot products. So it's the sign of, let's call it R1I x prime I plus the sum over all j not equal to I of that dot product. So R1j dot with x prime j, the sign of Ri2 x prime I plus that sum of j not equal to I of etc. Okay. So let's look at this. What is the distribution of this? Okay. So remember I said that little n is odd. So here we're summing over all the indices except for I. So that's an even number of indices, right? So we have a dot product of an even number of terms here. And it's a symmetric random variable, right? It's just as likely for this sum to be L as it is for it to be minus L. Because in particular, if you have some configuration of RJs that give you L, it's equally likely that you got the negative of all those RJs, and then you would get minus L, right? So conditioned on not being 0, plus, minus are equally likely. And furthermore, since there's an even number of terms here, this sum has to be even. Does that make sense? You're actually, because each term that you're adding is odd. It's either +1 or -1. It's odd. You're adding an even number of odd things, so the sum has to be even. So not only is it equally likely to be plus or minus, but whatever it is, if it's not 0, it's at least 2 in magnitude. Meanwhile, this part here is equal to 1 in magnitude. So if that black circle sum is not 0, then whatever sign it has will determine the sign of the whole thing. Okay? Only when that black sum is 0 does that yellow part even matter. Does that make sense? Yeah?
Yeah.
Okay, good. So, and so let's focus on that. Let's say that the sum in the black circle is 0. Then what can we say about the yellow part? If the black circle is 0, then there are two cases. Either xi prime is +1 or xi prime is -1. Remember now, we're comparing that yellow circle with this yellow circle, because we're looking at Hamming distance. So the question is, are these two things going to be the same or different? If xi prime is 1, it's going to keep it the same. If xi prime is -1, it's going to flip it, right? So basically, you can think that if you compare, now let me put it in red. If you compare this entry with this entry, kind of most of the time, it's just randomly equal or randomly different 50-50. Like basically, as long as the black sum is not 0, it's just 50-50 different or same. But in that small percentage of the time where the black sum is exactly 0, I either bias myself to equal the entry of B, or I bias myself to be different from the entry of B based on whether xi prime is equal to +1 or -1, which basically is the same as based on whether xi is equal to 0 or 1. So whether or not the ith bit, that ith bit of x were 0 or 1 will introduce a bias one way or the other. Okay, and Stirling approximation, I mean, when is this black circle going to equal 0? Basically, the amount of, it depends on exactly, let's just, let's consider the case where all the xj's there are 1s. Every other case is basically is going to follow the same kind of argument. If all the xj's are 1, then for that black sum to be 0, exactly half of my rj's have to be 1, and exactly half of them have to be -1. And you could ask, so what's the probability of that? The probability of that is roughly n choose n over 2 divided by 2 to the n, because the total number of r's is 2 to the n. The total number of r's that have exactly half of their bits as +1 is n choose n over 2. And Stirling says that this is roughly 1 over root n. Okay. So I'm basically either biasing myself. So either those circled red bits are equal with probability about half +1 over root n, or unequal with probability roughly 1/2 +1 over root n. Right? So I'm biasing them by this 1 over root n. And then if you repeat this many times, kind of an expectation,
Jelani, should that be 1/2 minus 1 over root n?
Well, I said unequal with probability. Yeah. So if I had said equal, then I agree with you. If I had said equal, then it would be 1/2 minus 1. So they're either equal with probability half plus 1 over root n, or 1/2 minus 1 over root n. Sorry, the reason I put them both plus before because one of them said unequal.
Okay, got it.
So an expectation, the expectation of the Hamming distance between A and B is either n over 2 minus root n or n over 2 plus root n. Or not capital N. Let me actually say this differently. Capital N over little n, capital N over little n. Does that make sense? So if I pick something like capital N to be, I don't know, 10n or something, or actually then I have to put 10, but give me something, I don't know, 9n. Do I want 9n? So yeah, it doesn't matter so much, but I mean, the point is then I can say that so then this becomes basically capital N over 9. This becomes capital N over 9. So then it's like n over 2 plus or minus basically, 3 root n or something in expectation. It's either n over 2 plus 3 root n or n over 2 minus 3 root n. And then I can apply Chernoff to say that my deviation, Chernoff bound will imply that the deviation from the expectation is also on the order of root n with high probability. So therefore the gap will be either n over 2 plus root n or n over 2 minus root n. Does that make sense? So this is all just an expectation. So what's the probability that the Hamming distance deviates from its expectation by more than, let's say, root n? This is at most something by Chernoff. Okay, so that'll say that I deviate. If I deviate, so with high probability, I'm not going to deviate by more than root of capital N. So instead of n over 2 plus or minus 3 root n, now it's n over 2 plus or minus 2 root n. But I still have that root n gap, that root capital N gap. Okay, so that's basically it. And then I think I only have about 3 minutes left. I do want to say something about the lower bound for indexing. Questions about this before I talk about indexing?
Wait, so just to be clear, the point is that like if you're biased above n over 2, so if you're like n over 2 plus like root n or plus 2 root n, then that's the same as having xi is equal to plus 1, which means xi is equal to 0.
That's right.
Okay, got it. Thanks.
Okay. Yeah, so whether or not xi is 1 or 0 is going to affect whether or not the bias is going to be kind of a half plus root n or half minus root n or half plus 1 over root n bias versus a half minus 1 over root n bias, which ultimately with high probability will affect the Hamming distance between A and B, and it'll be the Hamming distance will high probability be in one of these two regimes. So if my algorithm can tell me, if my communication protocol for gap Hamming can tell me which regime I'm in, I then know what the bias was, and then therefore I know what the ith bit of x was.
Wait, why does it bias it?
I'm sorry?
Wait, why? Well, what's making them more or less likely to be equal?
Yeah, so the point is, right here in this yellow circle right here,
Yeah.
if xi prime is minus 1,
Yeah.
that biases me for each entry of A to be slightly more likely that that entry does not equal the corresponding entry in B. Right? Like if this part were not here at all, then what's the probability that A1 equals B1? It's 50-50, right? Because it doesn't even matter what B1 is. A1 is 1 half the time and it's minus 1 half the time. Right? Does that make sense? Like this black circle.
I thought you said that had to be even. What?
Yeah, but this black circle here is, I mean, okay, sometimes it's 0, but if you ignore the times when it's 0, it's either positive or negative, and it's positive half the time and it's negative half the time. Okay, and so kind of the sign of it is plus 1 half the time and minus 1 half the time. It's not affected at all by Ri, right?
Yeah.
So
okay.
So this is not biased. It's just basically contributing 1 to the Hamming distance half the time, and it's contributing 0 to the Hamming distance half the time.
Yeah. Okay.
Okay, but then there is some chance that black circle is 0.
Yeah,
And when
because
that black circle is 0, the part that I circled in yellow comes into play and introduces some bias one way or the other.
yeah.
And
'Cause-
if xi
I
prime
think
is
yeah,
1, it's biasing it to then that means that yellow part is always going to be equal to the b1. So it's going to bias me toward being equal to b1. Whereas if xi prime is -1, it's going to bias me to be different from b1. And by Stirling this part here, I know that the bias that's being introduced is on the order of 1 over root n in terms of the probabilistic bias.
Yeah.
Okay. Or if I,
Yeah.
if you want to write it this way, what's the probability that A1 is equal to B1? Let me call this term, let me just call these terms, this part is capital A and this part is capital B. This is equal to the probability that A1 is equal to B1 given that B is not 0 times the probability that B is not 0 plus the probability that A1 is equal to B1 given that B is 0 times the probability that B is 0. Okay? And the point is, this part here, the probability, given that B is not equal to 0, the probability that A1 is equal to B1 is exactly equal to a half. Exactly a half. And what's the probability that B is not equal to 0? It's roughly 1 minus 1 over root n. What's the probability that B equals 0? That's roughly 1 over root n. What's the probability that A1 is equal to B1 given that B is 0? Okay, this is either 1 if xi prime is equal to 1, or it's 0 if xi prime is equal to -1. Does that make sense?
Yeah. Yeah.
So this is the calculation that I was doing. Okay. And I think I'm, okay, so I'm actually out of time. So I think what I'm going to do is, I'll just, the notes, the proof that indexing is hard will be in the notes. You can take a look at that. And then Monday we're going to get started on what I told you we're going to get started on, which was, which we didn't get to, which is, where is that? Turnstile model. I do want to talk about that. So we're going to start that on Monday. So any other questions before we wrap up for today?
This proof is in the notes already?
Yeah, the notes for today have not been uploaded yet, but they will be uploaded soon, and this will be in there.
Okay, thank you.
Okay, so I'll see you all Monday then.
Thanks, Professor.